Okay, good morning, everybody. Welcome to our virtual joint conference for the National Weather Center Summer Research Interns. Today, we'll have final presentations from 5 of the National Weather Center Research Experiences for Undergraduates program scholars. On Monday, we'll also have 2 NOAA Hollings scholars presenting. So my name is Daphne Ledoux. I'm the director of this program. I've been the director since 2001. This year I brought in Alexandra Marmo, and she's been helping me run the program and has done a fantastic job. This program is funded by the National Science Foundation. NSF has been funding REU programs since the 1980s, and I actually did an REU in nuclear physics in 1988 when I was an undergraduate, so that kind of dates me a bit. We started our funding in 1991, led by Bill Beasley and others in the School of Meteorology. We had a couple years skipped, but we've had almost 22 straight years at this point, with a nice run of 4 or 5 grants in a row. We've had a total of 8 grants, and a total of over 270 students have come through this program. So these programs are designed to bring bright undergraduate students in from around the country to join our organizations and see what research is really like. This year, our 12 students are from all different universities, and they've joined us from as far as Puerto Rico and California. Hi, Elisa. One of our presenters today is in California. Unfortunately, we were not able to share a summer together in Norman, but we have gotten to know each other through GroupMe and lots of Zoom meetings. Our mentors are from 11 different organizations this year, including the university's Cooperative Institute for Mesoscale Meteorological Studies, the Advanced Radar Research Center, the Center for Autonomous Sensing and Sampling, and then both the School of Meteorology and the Department of Geography and Environmental Sustainability. We also have mentors this year from NOAA's National Severe Storms Laboratory, the National Weather Service Forecast Office in Norman, the Storm Prediction Center, the Warning Decision Training Division, and the Global Systems Laboratory in Boulder. So we've got a virtual mentor that would have been virtual no matter what. And then we also have someone from the Oklahoma Climatological Survey, Oklahoma Mesonet, and honestly, Brad, I'm not sure if that's one and the same or what. I think there's some distinction there, but anyway, I appreciate that you've been involved in the program this year as well. So to everyone attending today, what we're doing are talks in the format of the American Meteorological Society Conference, which is fairly common. It's a 12-minute presentation followed by a 3-minute question and answer period for each speaker. So please remain muted and hold all questions to the end. At that point, we ask you to just put a little Q in the chat so the moderators know that you are wanting to ask a question. And then they'll call on you to unmute your mic and ask your question. Okay, so to the students, I know I've said this already, but these talks can seem kind of scary, but they're also exciting. Scientific conferences are a great way to share what you have found through your research and get feedback from others in the field. It might seem scary and all that, but I hope that you're excited about what you did this summer, and we are excited to hear what you have done. All right, so now I'm going to hand it over to our moderators, Bryony, Puxley, and Kevin Thiel. They are current graduate students at the School of Meteorology. So take it away.
Hey, everybody. Thank you all for coming here today and for this talk. We have 5 wonderful talks that are on our plate for today. Everything from lightning to radar to boundary layer and more. So I'll be doing more of the question kind of sessions after each talk, and then Bryony will be giving the introductions before each one. So we'll kind of be tag teaming both ends of each presentation and having this kind of go along quite smoothly as we go. So I'll go ahead and turn it over to Bryony, and she can introduce our first speaker for today.
Okay, so as said, my name is Bryony Puxley. I will be introducing the speakers today. And first up, we have Hayden Webb. If you want to go ahead and share your screen, Hayden. While he's getting his screen shared, he'll be looking into an investigation into the characteristics of lightning as it interacts with towers. And once you're ready, Hayden, go ahead and take it away.
Okay, thank you for the introduction. This summer, I've been doing research with Dr. Kristin Calhoun and Dr. Darrel Kingfield. This research was also supported by NSF. It is widely understood that lightning is attracted to tall objects. However, a tall structure may be contributing to the increased lightning counts in its area as lightning interacts with the structure. Lightning that interacts with these towers can take the form of a traditional flash, but can also originate from the tower itself, and this is known as upwards lightning. We know that upwards lightning is lightning that propagates from tall objects and travels in an upward direction. We also know that it is often preceded by a cloud-to-ground strike in its vicinity, but little else is known beyond this. Our research aims to better understand the nature of upwards lightning and examine how lightning that originates from towers differs from that of a traditional flash. Before we continue, I think it's important to establish the motivations behind this work. The research primarily aims to examine the nature of lightning physics and has many potential applications, the foremost of which is improving lightning detection, which currently cannot tell the difference between upwards lightning and different types of lightning. It is also unknown how much upwards lightning contributes to the overall percentage of lightning, and determining this could help us understand how upwards lightning contributes to issues like global warming and could better inform tower construction and tower safety. As a part of our research, we are examining 10 FCC communication towers across Oklahoma, as shown on the map, each of which are mostly located in central Oklahoma. This provides a more reliable and detailed view for this centralized area. We're also examining towers at a variety of heights between 300 and 550 meters, as indicated by color here. As this research is very analysis focused, I think it is important to get a good feel of our work, methods, and data collection. The data for our research is collected from two main sources, the National Lightning Detection Network, or NLDN, and the Lightning Mapping Array, or LMA. Originally created in 1983 and upgraded again in 1995, the NLDN detects the very low frequency radiation given off by lightning return strokes. The NLDN then gives a single point for flashes detected within the range of the tower, which we can then use to filter the flashes down to ones that meet our criteria, such as date, month, or proximity. For this research, we're specifically looking for flashes that enter 1 kilometer of the tower and occur during the months of January, February, May, and August of 2010. Once a specific flash is collected, we then move into the LMA data. The LMA detects the very high frequency radiation given off by lightning as it creates new channels as it travels. We can then use these high density amount of points for a much more detailed view of individual flashes. We can then use a computer software to map the flash itself and attempt to manually classify it. For this research, we're using 4 main different types of classifications. A cloud-to-ground flash, or CG, which is lightning that starts in the cloud and then moves down and makes contact with either the ground or a tall structure. There is in-cloud flash, which is a flash that begins in the cloud and never makes contact. We also have lightning-triggered upwards, which is that upwards lightning that immediately follows a nearby cloud-to-ground strike. And finally, we have self-initiated upwards, which is upwards lightning with no cleared trigger, as we can tell. Here's an example of the software we are using to map the LMA data. To be able to classify these flashes, it's important to look at all the different fields that the software provides. The topmost box is an altitude over time chart, and in this case, we can see that the flash began at a very high altitude and moved down over time. We can then look at the middlemost box and the bottom right box, as they are both cross-sectional views of the storm. In this case, we can again reinforce that idea that it began at a high altitude and moved down over time. And we can also see that it moved towards the tower. And then finally, in the bottom left box, we have a bird's eye view of the flash. And in this case, again, we see that it originated away from the tower and moved towards it over time. Combining all this information, we can tell that this was most likely a traditional cloud-to-ground strike that potentially even made contact with the tower itself. Now that we've established kind of the process for classifying each flash, we can quickly walk through an example of each different type. Here's an in-cloud flash, and looking at the altitude over time alone, we can see that it maintained a very high altitude and never really went low enough that it could have contacted. Next, we have a lightning triggered upwards, which if you look at the bottom left bird's eye view, you can very clearly see the distinction between the two flashes, as you have the first one up in this blue-green area and the preceding flash in the oranges. Also looking at the altitude over time, we can see that that beginning of that second flash began at a much lower altitude and quickly spiked upwards and would be classified as a lightning triggered event. And finally, we have a self-initiated upwards. Looking at the altitude over time, we can see that it started at a very low altitude and directly over that tower. And without any other events occurring beforehand, we can see this was most likely self-triggered. Once we have classified all of our flashes, we ended up with 40 individual flashes to work with. We began by incorporating radar data and collected this data from the stations that best suited each tower. And for most of our cases, this was the Oklahoma City KTLX system. But for 3 of our towers, we also needed to use the Frederick, Oklahoma KFDR station. This data was then processed by the Warning Decision Support System, which was then used to create animated GIFs of each flash, which we could then overlay that LMA data to see how this flash appeared during the storm. This is the image of that traditional cloud to ground strike that we saw a moment ago. It is important to note that the radar really offers a new perspective to the flash. It allows us more things to consider its origin. In this case, we can see that this is a single-celled storm. And here's just that still frame of the flash mapped over the part of the storm in which it occurred. Notably, it happened in the very center of this cell and moved outside of the storm towards the tower, as indicated by the black circle. Here we are going to walk through a few examples of the other types of flashes. In this case, we have another cloud-to-ground strike, but this one occurred during the winter. Notably, this flash occurred right above freezing, and there was some freezing rain as a part of this storm as well. Here is a summer in-cloud flash that occurred in another single-celled storm. And finally, we have a lightning-triggered upwards flash as a part of a multi-cell storm. Again, here in the still frame, you can see the very distinct separation between the original flash in this blue color and the secondary flash from the tower in this purple color. We then attempted to quantify the data and make some overall observations. And overall, we see that cloud to grounds, or CGs, were the most common type we recorded, with self-initiated upwards being the least common, with only one recorded case. We then examined distance to the average initiated tower, the average initiated flash for each type. So we noticed that regardless of type, they seem to have very similar distances, with the exception of self-initiated, which this is what we'd expect, considering that self-initiated has no preceding lightning and then originates from the tower itself. So we'd expect that distance to be very small. Then, in a similar vein, we look at how distance affects the overall proportions. And if we look at the flashes that originated within 5 kilometers tower, we see that the proportions remain roughly the same, with in-cloud flashes and lightning triggered upwards tying each other. And while self-initiating upwards does increase in proportion, this is largely due to a decreased data pool. It is still only one flash that we recorded. Next, we examine the impacts of seasonality. We generally see that the summer had a lot more activity, as you would expect. Due to the lack of data, it's hard to draw much from seasonality, but it further reinforces that CGs have overall dominating the other flash types. Upon accounting, when examining the amount of LMA points for each type, we do notice that winter flashes seem to have far more LMA points for each flash. This could partly be due to the storms occurring at a much lower altitude during the colder seasons, but further data would be needed to be certain. Upon accounting for outliers, we continue to see that summer lightning has fewer LMA points, with lightning triggered upwards having the fewest, followed by CGs. Again, this image is important to note that with only one self-initiated upwards recorded, it's hard to draw much about its qualities from this. In conclusion, we offer a few of the total averages from our data. Again, we noticed that CGs were the most common type compared to the rarity of self-initiated upwards. Flashes began on average of 8.19 kilometers away from the tower, with an average time of 0.65 seconds, and each flash contained on average about 480 LMA points. It's important to note that our research is more of a starting point for tower lightning research. More data would be required for true statistical analysis. And generally, we're hoping that this lack of data and the difficulty at collecting it really shows the importance for improving these lightning detection systems. Thank you very much. That is all that I have.
I can give a round of applause for our speaker. All right, great presentation, Hayden. So at this time, if you have any questions, feel free to drop a Q in the chat. And then after that, I'll then call on you and you can unmute yourself and then ask your question. Our first question, Jeremy, if you want to ask that question, or if you want to take a second, and then I can say it too.
Hayden, I agree. Excellent presentation. Wanted to ask the towers that you had looked at that you were gathering data from, were they generally similar in construction, or were there any obvious differences that you could already see from just the sites you were looking at?
Yeah, well, thank you, Dr. Everett, for making it. I'm glad you got the invitation, but generally they were all the FCC communication towers, and so from the data that I've seen, they're all the same type, but they were created throughout a variety of years, so I cannot say for certain what the differences across the towers would be.
All right.
Thank you.
Ted, I'm going to ask your question now.
Yeah, sure. Again, nicely put together presentation. I'm Ted Mansell. I'm at the NSSL, and I was curious about your self-initiated flash that happened in the summertime. And do you know, did you look at any of the radar velocity data to see if there were particularly high winds with that? Because my understanding is that these tend to happen when there's strong winds to kind of carry away the corona current that comes off the towers that tends to prevent self-initiation.
Yeah,
so I was curious if you looked at the winds at all.
Sadly, we did not get to that part. It was something that had been brought up, but
okay.
The self-initiated was actually in a strange case because it was a part of our May flashes, which we didn't actually have time to get the radar for those that month. And so all the radar images from the other months that we looked at. So it's something that we had mentioned, but had not had time to get to.
Yeah, that would be interesting to look at, especially in the summertime. I usually think of these as being winter phenomena.
All right. And for our last question, I will turn it over to Tyler. If you want to ask your question now.
Hi, Hayden. I'm Tyler. I'm Alicia's friend. I go to SJSU. Our department chair sent out this link, so I was able to watch all your guys' presentations. My question is, I'm super fascinated about your research and about lightning, and you got to do all your research in Oklahoma, so it was all on flat land. So my question is, how do you think it would change if you were doing your research in areas of terrain, like if you had towers like maybe you had a tower on like a mountaintop or something like that, how terrain would affect your research? Just a curious question, because in Southern California we have a lot of mountains, so I just throwing it out there.
No, yeah, that is a great question, because one thing we wanted to look at, again, kind of got pushed away because of time requirements, was how the different types of lightning change over altitude. And so it would be very interesting to look at a tower compared to a flat area compared to a tower on like a mountain. If there's different flash types are more common there versus everywhere else. And that is something that we did want to look at, and we may still have time before the paper. It may still have time to be able to put that into the paper, but I do not have an answer for you right now.
No worries. I just wanted to, because I think it would be interesting, like, because you got the monsoon season right now. If you were to do a little research, like in the mountains of northern Arizona, I bet you'd get some really interesting data.
All right, let's thank our speaker one more time and give another round of applause. All right, and I'll turn over to Bryony for our next speaker.
Thank you, Hayden. That was a great, very interesting. I know there was so many different types of lightning. Next, we have Michael Lavallee. If you want to go ahead and share your screen, Michael. He will be presenting on radar rainfall estimates versus the Oklahoma Mesonet rainfall measurements.
All right. Can y'all hear me and see my screen?
Yes, we can.
Yep. Okay. All right. Thank you for that introduction. Just wanted to real quick give a thank you to my mentor, Dr. Brad Illston, for his guidance along with this project, as well as Daphne and Alex with leading this program and the NSF funding it as well. So why does a project like this matter? Having accurate radar estimating products is important because it aids in flood forecasting. Having those accurate radar estimates enables the forecasters to put out those timely warnings and advisories, because a lot of areas just don't have a dense gauge network that has that data available quickly. And with it, flooding being the second leading cause of death, weather-related cause of death in the U.S., that is something that's important. There's also applications in hydrological modeling and agriculture applications. So some prior research that goes along with this study. There's a study that looked at a single watershed in northern Mississippi, and it investigated 30 storm events there, and it suggested a majority of the radar estimates were underestimates of the gauge amounts. And so that kind of correlates, or not correlates, but it's related to my study here, because the precipitation estimator product that we use comes from a watershed forecast office. So it's kind of the same thing. And then, but accuracy within radar estimates isn't completely insurmountable, because simple methods like distance correction and field bias correction can significantly reduce those radar estimation errors. And then also there's a larger margin of error during the summer compared with the winter. So we kind of want to see if that's something that is repeatable or not. So some research objectives that we have is, how does distance from radar affect the rainfall estimates? You would assume that closer is better, but is there a range? Is it linear with how bad it gets farther out? And then also, is our errors in rainfall linear with respect to amount? Now you would imagine that whenever it rains 10 inches and you miss, the radar is underestimated by an inch, that's 10%. But if it rains 2 inches and it misses by an inch, that's 50%. So we kind of want to see, does it follow by percentage, or is it measurable like that? And then, do different seasons lead to different margins of error? So this figure that I have over here, I don't know if you can see the outline. I don't know where my mouse is, but the outline there is the ARRC's forecast area, the Arkansas Red River Basin Forecast Center. And so their radar product comes from the NextRad radars located within it, and it encompasses all of Oklahoma. Their precipitation estimator is called the P3, and it is gauge corrected. It is corrected from the Oklahoma Mesonet gauges as well as the Kokoros gauges, and is comprised of the 4-kilometer pixels. And the gauges that I will be using come from the Oklahoma Mesonet. There are 2 tipping bucket gauges at each site. Neither one of those gauges have a heater, so any kind of frozen precipitation that falls is not measured at the time, and it's not going to be until that precipitation melts on its own. So there could be some errors built into that. And then we will be adding up the days into months, and so we look at the previous daily totals, which is loaded into the 0Z file of the next day. And the time period that we're going to be investigating is 2010 to 2019. That way we just get a good amount of time in there to compare those products. And then so with this map here I created, it shows the sites. The red dots indicates the Mesonet locations that we picked. And then the colors is from the NOAA radar coverages. I'm talking with somebody through NOAA. Green is best coverage, yellow is better, fair is blue. And then how they qualify those is with radar beam availability. best is to 4,000 feet, better is 6,000 feet, and fair is 10,000 feet, whereas max goes out to the maximum radar coverage of 230 kilometers. And then I also tried to pick sites that only had coverage from one radar and there wasn't overlapping, radar coverages. That way we're just kind of looking at one radar to see if that makes a difference. And then picking sites going from the wet areas of Oklahoma down in the southeast to Oklahoma Panhandle where it is drier. And then, so this table shows some of the site descriptions of where we picked, and then try to start out from about 30 kilometers from the radar site. Didn't want to be right next to the radar because a lot of times you have a lot of ground clutter right next to it, and there's some artifacts. So I didn't want to have that affecting the precipitation estimator. And then within each radar coverage, I try to pick a dry and a wet site. So one would generally be on the east side of that radar, and one would be on the west. Okay, and then once we started looking into the data and compiling it for the months, started to see some really large overestimation errors or just large errors. So we started to remove some of those months where either the Mesonet gauge data or the radar data was missing or questionable. And these typically happen during the winter and or the distant and dry stations. Not exclusively, but that was the majority of it. So one example of one of the errors that I took out was for Carmago, which was in the fair category for October 2012. The radar estimated 33 millimeters of precipitation, and the Mesonet gauge only measured 0.5 millimeters, which was a 6,000% error. And so those were the kind of data that we removed. In total, we moved 14 months out of 960 that we looked at, and only one of those was a large underestimation. All the others were very large overestimations. And then, so with this table here, I averaged each of the months over that 10-year period for each one of the sites, and then took those averages there at the bottom. You see that underestimations are common in late fall and winter. And out of the 960 months that we looked at, 545 of them, or about 57%, were underestimations. So not as quite as high as the previous study that had 80%, but it does show a slight bias or slight majority towards underestimations. And then Boise City's large overestimate errors skewed the average, and it is as of note, it is the most distant and driest site. As you can see in some of those months, that is overestimation was over 100%. And so something like February or November would be an underestimation kind of a month, but because of Boise City, it skewed it. And another thing to note, the warm months are, I don't know about in Oklahoma, but in Texas, I would consider February sometimes a warm month. But starting in April through about August, most of the warm months are overestimations, except for May, which was the largest underestimation month. But May also has the most convective precipitation happens there. So that is, kind of eye-opening, is that whenever we have these large storms, or maybe if we had more time investigating whenever those large precipitation events happened over a short amount of time, does that lead to more underestimations? So you can see it happened even with the closest site as well, was underestimated. Okay, and then so this graph just visually shows you that other table where you can really see that the fall has the lowest average absolute errors, but also December and February performed fairly well. And then May down there really sticks out. Your overestimation for the most part, and then all of a sudden May just bottoms out. And also it was more common for sites to have large overestimations in the winter, even though they kind of averaged out lower. There would be several instances of really large overestimations that were not removed. Okay, moving on to looking at it from a distance standpoint. We did there is averaging for each one of the sites, and you can see that the dry sites have a greater absolute errors when compared within their radar coverage pair. And also, whenever you looked individually, the dry sites also had a larger range of errors. And then averaging both of them together, you can see that the average absolute error increases with increasing radar coverage or worse radar coverage, where it starts out with best at 8% error and then moves on to 21.6% for the max coverage. And I thought another thing that kind of stood out was for Hugo, even though it is distant, just about as distant as Boise City, it's the second wettest, and so its average absolute error was actually less than Cloudy and Holdenville, even though both of those are closer, but this one is wetter, at least than Holden. All right, so with this graph here, instead of doing it by the month, we've averaged out each one of the years, and it took its average, the absolute average error, and for the 10-year period. And then each one of the boxes with Shawnee and Guth, and then Holden and Hinton, they're ordered by their radar coverage. And so you can see by averaging these together that the average absolute error increases with the increasing distance, starting with best being the best, and then moving out to max, having the worst one. And then another thing, by doing it this way, again, it showed that the distant sites had more instances of the large radar overestimations as well. So finally, some takeaways. One thing that really stood out was locations that are close to the radar site and wet generally have the lowest absolute errors. It's important to have that wet part as well, because the drier sites, as seen in that other table, it would generally have worse errors. And so that could be the thing that if it rains 10 inches and you miss an inch compared to 2 inches, that's a smaller error. So, having more time, that would be something we could dig into more. And then with the P3 precipitation estimator that we looked at this product, that, radar estimation accuracy could really be improved for those distant sites by removing those really large overestimations, because once we started to pull this data, it's already supposed to be gauge corrected, or how they're supposed to correct them, and yet there are still these extremely large errors. And so just by, maybe somebody looking at those or whatever, taking those out, could really improve the accuracy, overall accuracy. And then in regards to that other study, winter did have a smaller margin of error compared to the summer, and then fall ended up having the best and spring being the worst. And so maybe spring had something to do too with there's more convective precipitation. So, but that's it. Any questions? Thank you.
All right, let's give Michael a round of applause. Thank you, Michael. All right, so feel free to drop your cues in the chat, and we'll go ahead and start rolling down through those questions as those come in. So give it a second. If no one has a question right now, actually, I'll go ahead and ask one to kind of get things started. First of all, I got a great presentation that's really interesting. Looking at this as kind of this multi-parameter kind of sense and all your different variables. So it was really well done. My question, though, is about the ARRC, if I'm saying that right. And you said it had a resolution of 4 kilometers. And I wondered if that resolution changes, how that might impact your results at all. I don't know how it would, but just out of curiosity.
So I didn't do this with each site, but at least initially with our initial results, what we did was, once we pulled up the data, like put in the longitude, or what was X and Y coordinates or whatever for each site, we ended up putting this positions right next to it to see how much it would differ. And most of the time the radar data didn't differ a lot. And so I think that ties more into, I guess, the curvature of the Earth is what Brad was saying, but also, with those pixels to see how much it differed between each, but they were similar. So I don't know if that answers your question.
I think so. Okay, thank you. All right, we have a question from Ben Schenkel. So if you want to go ahead and unmute yourself and ask that question.
Hey, Michael, great talk. I had a question about why May was so bad. I mean, is that just due to the type of rain that falls during that month, where it's very heavy and the radar struggles with that, or is it something else that that is not so evident?
Yeah, so like I said, I wish I had more time kind of digging into it more, but especially whenever you look, because I put them all in like spreadsheets, but whenever you look at the overall May, it was really severe with how severe the underestimates was. And then trying to look at the tables of which one, most of the time that it happened was during times of really heavy rainfall over like, couldn't see like the time period, but at least over a day. And so I do believe that is that convective precipitation that kind of leads to those more underestimations.
Great, thank you.
Michael, this is Dan Berkowitz. I posted on the chat. I'm wondering about the source of your radar information. Was that just the P3?
Yes, so the radar data that we used was the P3 precipitation product. I don't really know quite the methodology of how they come about it. Trying to figure it out, they just kind of said, well, it's gauge corrected and sometimes it's not. But yes, so the data that was pulled from it was for the ARRC's P3 precipitation product.
Okay, the main point I was trying to bring out is that relatively cool weather situations, there's so-called contamination from the melting layer. In other words, snow melting and picking up stronger reflectivities, hence overestimates from the radar.
Mm-hmm.
So I was just wondering if that was considered at all.
I don't really know. Well, I mean, like I said, whenever we looked at it, we took out some of those really large overestimations, but that's part of the reason why is because we didn't know if it was from melting precipitation or what caused those large overestimations. But yeah.
All right, let's give Michael another round of applause. Okay.
How do I stop? Never mind.
Okay. All right. And Bryony, for speaker number 3.
Great talk, Michael. That was very interesting. Next up, we have Elisa Guerrero. If you want to go ahead and share your screen. She will be looking into near-surface meteorological impacts resulting from a total solar eclipse. Once you're ready, just go ahead.
I always forget to unmute myself first and then go to the presentation. All right, hi everybody. Thank you, Bryony and Kevin, for hosting today's talks. So another thank you for the National Science Foundation for supporting my research this summer. And then I'd also like to thank Dr. Bradley Illston for supporting me through my research endeavors. So the total solar eclipse that I analyzed was on August 21st, 2017. It took place in the United States, starting from the northwest coast, heading towards the southeast coast. The main goal of my research is to quantify the reduction of solar radiation caused by the solar total eclipse and analyze the impacts of surface air temperatures. Another study that I did was between 2 resolution datas to see future data analysis on solar radiation and temperatures and see what would be best fit for those researchers. Some background for this specific solar eclipse event, there was 2 cases where in Kentucky who experienced 90 or 100% of the totality, and then in another case in the north central Oklahoma, which experienced an 89% totality. These 2 research papers discussed that there was solar radiation reduction and then also temperature reductions, but they didn't really touch base on temperature inversions that might have taken place during the solar eclipse in their locations. So some research on temperature inversions, between some cases, they said that there's stable equilibriums inside the layer. There's also a lack of circulation of air, and there is an increase of air pollution depending on the location. If you look onto the right of this graph, you would see the typical, how you would say like lapse rate. From A to C, you would see with height increasing, you'd have a decrease in temperature. But with temperature inversions, when you have a height increase, which you would see at B to C, and an increase in temperature, that's what it would be at an inversion episode compared to a lapse rate, which you would have on like typical days. The data that I used was from the Oklahoma Mesonet. I took 2 sites, one at Miami and another at Hollings, and I picked these 2 sites because Miami would be closest to its totality. I hope you guys could see my cursor. And then Hollings being down at the southwest corner of Oklahoma, being further from it 100% totality. The dates I analyzed were 10 days before and 10 days after, so from August 10th to the 31st. The time in UTC, solar radiation in watts per meter squared, temperature at 9 meters and 1.5 meters and degrees Celsius, and then also 5-minute and 1-minute data resolutions for the Miami site. The methodologies I took for my analysis is taking the average of the 10 days before and the 10 days after for each site in order to get a theoretical value for the day. And with that theoretical, I plugged it into a percent error equation, and the experimental value in the percent error equation resembles the actual observed value of the eclipse day. I am analyzing the specific times of the eclipse. So the eclipse maximum is when the eclipse is at its highest point, and that's given off of the solar radiation data, which is like watts per meter squared. And then the temperature inversion maximums will be in the degrees Celsius, where you would see the maximum inversions during the eclipse. I also did a time analysis during the eclipse for both stations on a timeline. You'll see that in the future. And then I also did percent error for the data resolutions, where 1 minute would be considered my theoretical value. So temperature inversion and lapse rates, how they're calculated is the change in heights divides into the change in temperatures at those heights. Whenever you have a positive value, you would have an inversion episode, and whenever you have a negative value, you have a lapse rate. Oops, I did not purpose or on accident. So then for my research, I had 2 heights specifically at 9 meters and 1.5 meters. And because those different heights didn't change much, there's a height constant of 7.5 meters. So when on the graphs, representation for the temperature differences at those heights are proportional to temperature inversions and lapse rate. For the Miami site, the actual and the theoretical solar radiation, when comparing the 2 on the graph right here, I also have, just a little side note, I also have the data on the bottom if you would like to see it numerically instead. But back to the graph, you could see that there was a big drop, so the actual is in the blue. It was a big drop from the solar radiation episode, from the eclipse event, and it was a 94% error from the theoretical, and then to the right you would see a temperature difference, a percent error being 195%. For the Hollings station, I did the similar analysis where instead I would get an 86% error in solar radiation and then an 111% error between the temperature differences. Between the Miami and Hollings site, I graphed them on top of each other so we could see that with distance, how they differ. So for the Miami, the highlighted blue is 47% drop, or 47 watts per meter squared dropped from the eclipse, and then for Hollis it went down to 114 watts per meter squared during the eclipse maximum. And here are like the rough estimates of how far away they are. So you can see like Miami is closer to the 100% mark, and then Hollis would be further away. Then for the temperature differences, the inversion maximum reached 0.50 degrees Celsius at Miami, where Hollis reached 0.10 degrees Celsius. Right here on this slide, you see the timeline that I created where Miami's duration for its solar eclipse lasted for 3 hours and 35 minutes. And so it started before and it way before Hollis, and then it also ended after Hollis. Hollis actually had a 2-hour and 30-minute solar eclipse event. And at the bottom, I have some data to see how long it took for specific times to be reached. So from the start of the Miami eclipse, it took 1 hour and 20 minutes for the typical lapse rate of the day to reverse. So that's when it would reach 0 and then change to positive values. So it took 1 hour and 20 minutes for it to reach 0. And then from the 0 mark, it took 30 minutes to reach its highest inversion. And it maintained that high inversion for 10 minutes. And then it went back and did a reverse for another 0 back to the typical lapse rate of the day. If you would like to go up to the graph or the timeline, you can see that this is the eclipse start, and then the 0, and then over here where you have the inversion maximum being reached, it actually overlaps the eclipse maximum. And it took a total of 5 minutes before and 5 minutes after, so a total of 10 minutes during the eclipse maximum. You're smack down watching the eclipse. Going down back to the Hollis data, it took 45 minutes from the start of the eclipse to reach the lapse rate reversal, and 5 minutes to reach the highest inversion episode, and it lasted there for 10 minutes, and it reversed back after 10 minutes. Comparing the data resolutions between 1 minute and 5 minute for Miami, graphically, they look very similar. They're right on top of each other. And then also numerically, during the solar eclipse maximum time, they also didn't differ that much. So if I were to change using 1 minute data compared to 5 minute data, they're relatively the same. So I don't think that it would change my analysis. So the conclusion, with distance being closer to the 100%, it extends the duration of the eclipse time. It also increases the solar radiation percent error compared to the theoretical values, and the temperature inversion strengths also increase, being closer to 100%. There's also the overlap between temperature inversion and then the temperature and the eclipse maximum. So that could have potential to influence health issues if you're an at-risk person or an individual, where if you're outside wanting to watch the eclipse right smack down in the middle, or it's the best time to watch, depending on where your location is, and if it's really highly polluted. This is another case that we'd probably want to study. And then for the resolution data, is when analyzing it for solar radiation and temperature and temperatures inversions, there's not much of a difference between the 1 minute and 5 minute data. But it's still recommended if you would like to look at the 1 minute data for other attributes. And then my appreciation, thank you, Dr. Bradley Illston again, Daphne Ledoux, and then Alex Marmo with the REU program.
Let's give Alicia a round of applause.
Okay.
All right. If you have any questions, make sure to put those into the chat. Punch in the letter Q and put it in. So, do we have any right now? I don't see any, but I can go ahead and get get the ball rolling on it. But yeah, I mean, first of all, great talk. That was really interesting. And I mean, not every day you have a solar eclipse that you get to use those kind of data sets from. So it's a really unique thing to be studying. So, I mean, there's going to be another solar eclipse in 2024 across the U.S. If someone wanted to go back and replicate that study or do some, would you have suggestions of like things to add to it, or like places to look, or just things like that for any kind of future studies?
I would feel like looking at like air pollution data would be something I would do for the second study. If I were on that study, I would definitely look at air pollution, and then to make my data more accurate, instead of doing a theoretical based off averages of the 10 days before and after, I would probably look more into like an astronomical look, where it gives you data straight from like angles of the solar radiation. Like I want to have more precise data on that end.
Okay, for your calculation of your and errors and those kinds of things. Okay, yes. Very cool. All right, we have a question from it was Darrel. So if you want to go ahead and ask that question, it is in the chat if you want to read that out too.
Yeah, I was just wondering, I'm just trying to wrap my head around the error percentage that was provided here. So this was relative to a normal non-eclipse day, or was this more of a theoretical eclipse passover with regards to these two stations?
So for the month of August of 2017, I took the 10 days before and the 10 days after. So it wasn't the specific day itself. It was just an estimate between the 10 days before and the 10 days after to give you that center of the 21st. So that was like the best thing I could do with the data. But if I would have probably used that type of data where it comes from the angle of the curvature of the Earth and all like that better high quality data for calculating solar radiation of the day, I think that would have been better, but that's how I did my theoretical. I don't know if I answered your question.
Yep, thank you.
Okay.
All right, one last call for questions. If you have any, make sure to whatever later. I think we'll go ahead and move on to our next two talks. So let's thank Alicia one more time. Really great. And I'll turn over to Bryony for our next speakers.
Great talk, Alicia. That was very interesting, looking at the solar eclipse that I was actually here for. So next we have a talk by Jordan Robinson. He will, if you want to go ahead and share your screen, Jordan, he will be looking at decoding the stable boundary layer, comparing lower atmosphere dynamics of Alaska and Finland.
Can everybody see my screen?
No.
No, not yet.
Yeah, there we go.
Okay.
There we go.
Sorry about this. Okay. Okay, thank you, Bryony. Hello, my name is Jordan Robinson, and my project today is decoding the stable boundary layer, comparing the lower atmosphere dynamics of Alaska and Finland. My mentors for this project were Brian Greene, Dr. Elizabeth Pillar-Little, and Francesca Lappin. And I'd like to give a thanks to OU's Center for Autonomous Sensing and Sampling, or CAS, the National Weather Center, and the National Science Foundation. So what is the boundary layer? The boundary layer is the part of the atmosphere that is most immediately affected by the forcings of the Earth's surface. This includes friction, radiative cooling, and also differences in elevation, among other variables, and it is known to be prone to abrupt changes in vertical wind and temperature bias. So the boundary layer can generally be classified into two conditions: unstable and stable. In unstable conditions, temperature decreases with height and air can easily rise, and you often have turbulence. And under stable conditions, temperature increases with height, and you have a laminar flow, and these conditions are most often in the polar regions and also at night throughout the globe. So why should we care about the boundary layer? Well, there is a large gap in measurements of the boundary layer, and this gap translates into the efficacy of our weather models. And we also know that there are couplings between the Arctic boundary layer and the mid-latitudes. So better understanding the weather in the Arctic boundary layer, we can better predict the weather here. And also, it's where we all live, so we should want to better understand it. So my question is, how do the characteristics of the stable boundary layer in far north Finland, right here, compare to that on the north coast of Alaska, all the way over here? So I'm going to be looking at two main sets of data. I looked at data from the 2018 Strategies for Observations in the Arctic Boundary Layer, or ISOBAR, field campaign. It was a month-long campaign in February of 2018 off the coast of Oulu, Finland, on the island of Paleoto, and incorporated the use of remote sensing and remotely piloted aircraft systems, or RPAS. Now I'm looking specifically at data from the CopterSign, which was a drone designed by CAS specifically for unmanned measurements in the boundary layer. I'm also looking at data from the American Radiation Measurement Project, their site in Point Darrel, Alaska, and I'm going to be looking at data from February of 2018. I'm going to be looking at radiosonde data. So although the boundary layer is a sublayer of the troposphere, the boundary layer itself is often made up of smaller layers. So you can have surface boundary inversions, where you have positive lapse rates at the surface, and the lapse rate being the rate at which temperature changes with height. You also have elevated inversions, which is an additional layer where the lapse rate is positive and is disbarred from the surface boundary inversion by a convective layer. And there's also stratified layers in which the lapse rate changes in magnitude while remaining positive. Here's an example of what a layered boundary layer would look like. So much of my research was based on the work of atmospheric scientists John Mayfield and Gilberto Toscezzato. They looked at over 3,000 radiosonde profiles from 2000 to 2009 over Fairbanks, Alaska, and they actually developed an algorithm to statistically analyze the presence of inversions in the boundary layer over Fairbanks. And they actually found elevated inversions at roughly 1,200, 2,100, 2,700, and 3,100 meters. And my mentor was actually able to recreate their algorithm, and I was able to apply it to profiles from ISOBAR and ARM. So how did the algorithm work? So the key ideas for the algorithm was, for each profile, a line was fit between 2 points, and then this process was repeated with the addition of a third point. And then this loop continued with additional points being added until the root mean square error was greater than 0.1. And once complete, we were able to determine the base and the slope of each inversion layer, provided one was present. And like Mayfield and Toscezzato, that we ended up with two main variables, ZB, which was the base of each layer, and M, which equals the slope or the lapse rate. And here's kind of an example of what my code looked like for the algorithm. Now on to my results. So both sides, an inversion and stratified layers were clearly present. However, there was persistent variability in the makeup of these layers over the observed days. Here, this is a profile from Finland. This is from February 18th and February 20th. As you can see in the beginning, you have an inversion that starts off at the surface, but it progresses and becomes restricted to the highest 150 meters in this particular profile. And looking at the profiles, I was able to generally classify them into general and classify them by how strong the inversions were in each part of the layer. So I saw that a plurality of the profiles from Finland and North Alaska there was a prominent upper level inversion, and also in Finland there was a significant minority of profiles in which there was a prominent ground inversion. However, this was less common in North Alaska, although over North Alaska there was a significant amount of profiles in which the lapse rate was nearly decreased at a nearly linear rate. There was also a significant minority of profiles in which the profile started off with an inversion. However, that inversion progressed into several stratified layers or isotrophic layers in which the temperature was roughly constant with height. And looking at potential temperature for both of these data points, I was able to see a common theme of tight gradients in potential temperature at around the lower levels, and they actually tended to be lower over North Alaska compared to Finland. And when I looked at the low-level wind environment, a prominent feature over Finland was a wind maximum at around 175 meters. However, over North Alaska, many profiles exhibited a much more gradual increase in wind with height. And this shows me that the boundary layer over Finland appears to be much more stratified. I also saw a frequent presence of dry air intrusions above the surface over the ARM data site. There are values of relative humidity as low as 30% with tight gradients with height. And here's a profile from February 6th over North Alaska. As you can see, there's a really moist layer at around 50 meters. And then there are several layers here of drier air, especially around 200 meters. The lowest value relative humidity I saw from data from the isobar campaign was roughly 50%, and this occurred at the surface on February 18th, 2018. Now, here are the results from my algorithm. So on the left, you have a profile from Finland, and then here on the right, you have a profile from North Alaska, and the black spiked line is the original temperature profile, and then the dashed blue line is the line that was fit to the profiles. So I saw that over both places, layered structure occurred 100% of the time, although over Finland, layers of 3 or more occurred approximately 93% of the time, with a maximum of 11 layers being recorded in a profile. Over North Alaska, layers of 3 or more occurred only 86% of the time, with a maximum of 10 layers in a profile. And looking at the base of the layer specifically, over here I have the base of the average base for each layer, and I noticed that the average height of the first layer for both sites is around 40 meters, and on average the average height of each layer is roughly 23 meters over Finland, and over Alaska, it was about 25 meters. And looking at the lapse rate, I noticed that in the first layer for both sites, the lapse rate was roughly 10 Kelvin per meter, and for comparison, the dry adiabatic lapse rate is negative 9.8 Kelvin per kilometer. So you have a very stratified environment over both places. However, I found interesting that over Finland, the lapse rate, there was a very decrease in the lapse rate with height. But over North Alaska, the lapse rate was was relatively constant after the first layer, being roughly around 4 Kelvin per per Kelvin per meter. However, with a notable exception of the ninth layer, in which there are two occurrences of a ninth layer being heavily stratified with a lapse rate of an average lapse rate of 28.3 Kelvin per meter. So what are the takeaways from this? So we can see that a layered structure is ubiquitous in the boundary layer. And despite climatological similarities, regional variations contribute to different realizations of moisture, wind, and temperature gradients. In addition to inversion layers, stratified layers are also frequent. I also noticed dry air intrusions were common at the top of the boundary layer over North Alaska. Although the depth of the first layer was similar for both sites, the depth of subsequent layers varied, and the slope of subsequent layers, there was greater variability in the slope of subsequent layers over Finland. So in terms of future work, I would like to potentially look at measures of stability over the two sites, specifically looking at Abikov length and Richardson numbers. Also, I think it would be good to look at the synoptic and mesoscale environments during the observed periods. And also, I would like to be able to apply the algorithm that we use to other available profiles over the Arctic around the same time period. Thank you. That's all I have today. And thank you all for joining.
All right, let's give Jordan a round of applause. Great presentation. All right, so let's see if we have any questions over here. All right, we have a question from Ben Schenkel. So if you want to go ahead and ask your question, unmute yourself there.
Hi, Jordan. Great talk. You did a lot of work there. Just had a question. I know this is beyond the scope of your study potentially, but do you have any ideas as to what the source is of those frequent dry air intrusions over Barrow, Alaska, the Barrow, Alaska ARM site?
Yeah, so I don't know specifically. I have an idea that it could potentially be perhaps dry air advecting from the continental regions, from maybe the mountains over Western Canada, or potentially dry air maybe advecting from vecting north from the poles potentially. But yeah, that was interesting. Yeah, that was a great question.
Thank you.
Okay, Eleanor Martin, if you want to ask your question now.
Hi, yeah. So this might also be a question for the next speaker, but if the Coptersun could measure anything else, what would you like it to measure to help you with understanding the Arctic boundary layer? I can see Liz laughing.
I guess it would be good if it, I haven't really thought about it. Potentially, maybe, I think it would be good if we could get measures of maybe Abikov length through the Coptersun. I don't know of all the capabilities of the Coptersun, but I think that would be a good thing. Brian, say more to that.
Yeah, no, everything you're saying is right up. I just anything more like turbulence explicitly related would be nice, but for these, yeah, everything you're saying is, I agree with Jordan.
All right, final call for questions. Going on. Okay. All right, let's thank our speaker, Jordan, one more time. Give him another round of applause. Great job. And now I'll turn over to Bryony to introduce our final speaker.
It's great talk, Jordan. That was very interesting. Last but definitely not least presentation for today is going to be by Teresa Linchek. If you want to go ahead and share your screen, Teresa. She is also looking at the boundary layer, this time quantifying the stable boundary layer depth in the Arctic region of northern Finland.
Okay, can everybody hear me?
Yeah, we can.
Awesome. Okay, so hello. Again, my name is Teresa Linchek, and today I will be sharing with you the work I have done with the Center for Autonomous Sensing and Sampling, as well as my mentors, Brian Greene, Francesca Lappin, and Dr. Liz Pillar, to try and quantify the stable boundary layer depth in the Arctic region of northern Finland. So giving a little bit of background, what exactly is a boundary layer? Simply put, you can think of it as the lowest 1 to 2 kilometers of the atmosphere that is directly influenced by the Earth's surface. So those influences can include incoming and outgoing solar radiation, friction forces. Overall, the boundary layer is very sensitive to these forces. So what we see is the boundary layer will actually evolve throughout the day. So you could, during the daytime when there's strong radiation, you'll actually get like warm pockets of air rising and mixing, and we say that it is a convective-driven turbulent mixed layer. However, during the nighttime, when those radiation forces decrease a lot, we see the creation of a much shallower boundary layer called the stable boundary layer, which is usually driven by a lot of weak and intermittent turbulence and shear. So, but more specifically, what exactly is the stable boundary layer? So again, I said it forms at night in the absence of surface heating from the sun. But what happens in this boundary layer is the Earth's surface will actually cool faster than the air above it. And that eventually causes the temperature to increase with height. And so we call these temperature increases temperature inversions. And when we get temperature inversions, we tend to see what are called stable conditions. So again, we get weak intermittent turbulence, weak winds, we see a lot of negative buoyancy, shear and subsidence going on, and then we often see the development of strong low-level jets above the stable boundary layer. So why do we actually care about the stable boundary layer? Well, they influence a lot of near-surface and large-scale atmospheric dynamics. Because we don't have a good grasp on the physical processes in stable boundary layers, they're subsequently poorly modeled in our weather prediction and climate models. Furthermore, like stable boundary layers tend to trap aerosols and like air pollution and negatively affect our air quality. And so you can see an example, I showed a picture over early morning in Scotland. Because there was a presence of a stable boundary layer, there was a lot of smoke that ended up being trapped and negatively affected the air quality. So overall, we need a much more in-depth understanding of the stable boundary layer. However, when we get into the details of trying to quantify the stable boundary layer depth, or like AKA the height, the definitions for the depth vary widely in literature and studies. And so there are definitions including temperature maximum temperature gradients. You see it being defined as the maximum horizontal wind speeds in the atmosphere. You see it as the top of the stress layer, and a bunch of other definitions. So really, scientists can't agree on how we should define the stable boundary layer depth. So with my research, I want to take observational data taken from the Arctic and try to best determine where we should define our stable boundary layer height. So what is the causes of this discrepancy or these differences in definitions when it comes to the stable boundary layer height? And the main problem comes from the fact that there is a severe lack of high resolution observations of our atmosphere. Like, it is known a lot in our community as like the boundary layer data gap. And the reason for this is quite simple. Our atmosphere is really big and our instruments can only measure so much. For example, if you launch weather balloons or like radiosondes, they only go about once or twice a day, and then the time they spend in the boundary layer is very small. Like, conversely, we have like LiDAR's equipment that has great resolution. However, they're very expensive and sensitive to the environment, so they're not a viable option for measuring the boundary layer. So how do we fix this? So we introduce unmanned aircraft systems, such as like remotely piloted planes and quadcopters. So luckily here at CAS, they've spent many years developing their own quadcopter known as the copter sonde. And with this copter sonde, they can specifically get high resolution profiles of temperature, humidity, pressure and wind speeds. And you can see on the right with this graph, it basically compares the amount of temperature data that we get from 2 radiosondes versus the amount of temperature data we can get taken from a copter sonde. So in general, though, all of the data I'll be using will be coming from the 2018 Innovative Strategies for Observations in the Arctic Atmospheric Boundary Layer campaign, aka the Isobar Field Campaign. And it was a field campaign that took place over 2 weeks in February on sea ice over the island of Honolulu, Finland. And during this campaign, most days we had 7 to 10 hours of daylight, meaning that there was strong surface radiation cooling, meaning that we had good conditions to form stable boundary layers. So within this field campaign, there was data taken from meteorological towers, ground-based sensors, and again, unmanned aircraft systems, or UAS, like our copter sonde. So the methods for my project specifically are, I was looking at a case study taken from February 8th, 2018, when there was strong radiational cooling and clear skies. So again, great conditions for stable boundary layer formation. And the picture in the background actually is from that night. And so I took data from the copter sonde flights, including their temperature, wind direction, and wind speed profiles. And then I investigated the profile behavior at the supposed stable boundary layer depths, including the maximum potential temperature gradients, or maximum temperature change with height, and the maximum wind speeds. So the first thing I looked at was the maximum temperature gradient. So you can see in these 3 graphs, it was all from the same night, different times of when the copter sonde flew in the vertical and took temperature measurements. You can see potential temperature on the x-axis, height on the y-axis. And what I was looking for is when did that temperature increase the most? And so the black line in each profile shows where I found that maximum temperature gradient. However, there were some difficulties trying to find this gradient. One, because the copter sonde has such high resolutions of data, when you do try to change the resolution and look at coarser or more specific or less coarse resolutions, you can get differences in where your maximum gradients actually occur. Also, if you don't filter out the first couple meters, maybe 10 or 20 meters, you can often get false positives. As you see in the 3rd graph, before I got rid of anything below 50 meters, I had a much lower stable boundary layer depth than after. So because of these small uncertainties, looking at the potential temperature profiles alone is not necessarily the best metric for determining our stable boundary layer height. So what I did was I added in the wind directions that were also recorded by the copter sonde profiles. And when I did that, I saw something pretty interesting. When what you can see is below and above where these supposed depths are, the wind direction actually changes, especially so for the first and second profiles. And so what I took away from this is that these change in wind directions could possibly be an added metric to figuring out how we can determine the stable boundary layer depth. And then finally, I looked at the maximum wind speeds. So again, on the x-axis, we have wind speed magnitudes, and then y-axis height. And then what I did was I found where the wind speed were maximum, and the black line in these graphs show that height. And then also the green line is that boundary layer depth that I found from the temperature gradients in the previous slides. And another interesting thing that I found was that consistently, the maximum wind speeds occurred about 100 meters above the maximum temperature gradient. So future work, I thought this is probably another metric we can add to defining our stable boundary layer depth. So some of the next steps I want to take with my work are to, 1, compare copter sonde profiles with the other UASs that were flown during the Isobar campaign. Specifically, our collaborators had 2 other copters, quadcopters, and so measuring their data compared to our copter sonde would be a great metric to check for reliability in our measurements. Also, I'd like to compare the UAS data to LiDAR measurements, being as again another metric for reliability, and then we could also look at more definitions of the stable boundary layer depth. So things like our mean wind speed variance, looking at the stress layer, etc. And then finally, I'd also like to investigate more parameters of stability to improve our understanding of what's going on in our case study, as well as like how we can define our stable boundary layer depth. And so some of those parameters, stability, include the Abakov lengths and the gradient Richardson numbers. So in conclusion, what I want you to take away from my presentation is, one, the stable boundary layer depth, still not well understood. It's very poorly measured. However, technology like our CopterSonde or other UASs can fill that data gap, and they can offer higher resolution temperature, wind speed, and direction profiles. And then also, so far, maximum potential temperature gradients by themselves might not be the best indicator for the stable boundary layer depth. However, combined with the horizontal wind directions and speeds, we might be able to have a better chance of defining what we think would be the correct height. And that is it. Thank you.
All right, give another round of applause for Teresa. Great presentation, and now we'll move on to questions. So if you have any of those, make sure to drop a Q into the chat. And all right, Eleanor Martin, fire away.
Thank you. I'm not going to ask you the same question, just because that would be boring. So, a philosophical question. Does the stable boundary layer just have one height? I mean, is there just one point that can define the height of the stable boundary layer?
That's a great question.
And I don't know the answer. So.
No, I don't have a concrete answer either. However, I think it really depends on the context of why you want to know the stable boundary layer height. For example, if you are really interested in air pollution studies, you might be specifically interested in, okay, well, where does that temperature inversion end? Because that is where you're probably going to find most of your aerosol concentration. However, if you're looking to like simulate the stable boundary layer in like an LES or other type of climate model, you might be looking at a different height because you're more interested in the turbulent actions that are taking place and where like convection occurs versus where there's like no convection and mostly like shear and like negative buoyancy, etc. So that was a great question. Thank you.
All right, Ben Schenkel, I'm going to ask you a question.
Hi, Teresa. That was a great talk. I just had a question. This is thinking maybe a couple steps ahead, but do you have any ideas about how you might optimally combine some of these different variables to come up with like an SBL depth that's, I guess, that's the most accurate measure? Or maybe you haven't thought that far ahead, but I'm just curious.
Once again, it's like what I was saying in the previous question, it really comes down to why do you want to know like the depth of the stable boundary layer. And I think for my purposes right now, I'm just trying to see what kind of definition can we obtain just using CopterSonde or quadcopter technology, because this is in essence a very novel or new way of profiling the boundary layer that we haven't really seen before. And so I think it'd be pretty cool to just say, okay, we can take our quadcopters or our UAS technology and get one like definite definition just from that technology that we can compare to other instruments and simulations.
Okay, thank you. Yeah.
All right, any final questions? All right, let's thank our speaker, Teresa, one more time. Give another round of applause. All right, and that was our last speaker for this session. So really great job, everybody, across all 5 speakers that we saw today. Some really interesting, high-impact work and really well done. So congratulations to all of you guys on a really great presentation and studies. And I guess I can throw it over to Daphne or Alex to kind of send us away and wrap us up.
Yeah, thank you, Kevin. Thank you, Kevin and Bryony, for running our sessions today. I really appreciate it, and everybody did a great job. Thank you to everyone who attended today. Thank you all so much for your support of the interns this summer. It means a lot to them, especially this year when they might not have had an opportunity at all. Even being miles apart, everyone has helped them understand research and what it is all about, and helped them with that experience and helped us think about what careers in research can be like. These programs wouldn't be possible without all the organizations and mentors and everyone else who brings ideas to the table, so thank you all so much for that. Thank you to everyone who helped make this year a special one. And then our next session, we have one more on Monday. I hope you all can join us again. It'll be Monday at noon Central Time. I hope you have a great afternoon, great weekend. Bye, everybody.